Today, we're diving into event handling using Kafka with Spring Boot microservices, a crucial topic for modern software architecture and development. Event-driven architecture, or EDA, is an architectural pattern where decoupled services communicate asynchronously through events, forming the backbone of responsive systems. Microservices are small, independent services focusing on specific business functions. Combining them with EDA yields applications built as collections of loosely coupled services that communicate through asynchronous events. One of the primary benefits is decoupling, where services interact via events, significantly reducing direct dependencies and allowing independent evolution. This decoupling allows services to evolve, scale, and deploy independently, enhancing overall system flexibility, resilience, and faster development cycles. EDA also enables real-time processing and horizontal scalability, allowing independent services to scale as needed to meet fluctuating demands. In this model, microservices act as event producers or consumers, or both, with an event signifying a state change in the system, like an order being placed. Event producers create or trigger events, while event consumers react to those events, with an event bus serving as the central communication channel, ensuring reliable delivery. Applications requiring fan-out or parallel processing greatly benefit from EDA, as a single event can be consumed by multiple microservices simultaneously for diverse actions. However, challenges include increased complexity in managing event flows and ensuring data consistency across distributed services, which requires careful design. Apache Kafka is a distributed event streaming platform that enables scalable, fault-tolerant, and real-time data processing for high-throughput scenarios. It acts as a central message broker for microservices, facilitating efficient and reliable communication across your entire distributed system. Kafka's publish-subscribe model enables asynchronous and decoupled communication, where producers publish events to topics and consumers subscribe to relevant ones for processing. Key features include horizontal scalability, achieved by adding more broker instances to the cluster as your data volume grows. Kafka also ensures fault tolerance and durability through its replication mechanism, where events are replicated across multiple brokers to prevent data loss. Furthermore, Kafka can retain events for a configurable duration, allowing services to replay events if necessary for recovery, auditing, or new feature development. In microservices, Kafka provides significant benefits like enhanced decoupling, allowing independent evolution and faster development cycles for each service. Its architecture supports high scalability and elasticity, along with robust fault tolerance and durability, making it ideal for complex, mission-critical systems. Spring Boot simplifies building production-ready applications, and the Spring Kafka project offers powerful abstractions and utilities for seamless Kafka interaction. To implement event handling, first, set up Kafka, ensuring Zookeeper is running, then create Spring Boot projects for both producers and consumers. Add necessary dependencies like Spring Web and Spring Kafka to your projects, and configure Kafka broker addresses and other properties in application.yml or application.properties. For producers, use Kafka template to send messages to Kafka topics, simplifying the event publishing process with minimal boilerplate code. Consumers utilize that Kafka listener annotation to define methods that react to events from specific Kafka topics, enabling event-driven logic. The event itself is the message sent from the producer to the consumer, representing a specific state change or action within the system. Consider an e-commerce application where placing an order triggers an order-placed event, a common scenario in distributed systems. The order service publishes this event, and other services like inventory management and payment processing consume it to perform their respective tasks. For practical implementation, the producer publishes order events to a Kafka topic when a new order is created via its API. The consumer then consumes these order events from the order-created topic to process payments, ensuring timely financial transactions. Additional considerations include using a standard message format like JSON or Avro for interoperability and implementing robust error handling with dead letter queues. Common configurations include Bootstrap servers for Kafka broker addresses, Group ID for consumer groups, and proper serializers/deserializers for message format handling. Kafka-based event-driven microservices offer immense advantages, including high scalability, capable of handling millions of events per second with ease. Data replication across brokers ensures resilience, preventing data loss even in case of broker failures and maintaining system integrity. Asynchronous communication leads to faster response times and a better user experience, while loose coupling makes the system flexible and easier to maintain and evolve. Kafka's architecture ensures fault tolerance, keeping the system operational even if some services fail, and enables real-time data processing essential for modern, dynamic applications. Mastering event handling with Kafka and SpringBoot empowers developers and architects to build highly scalable, resilient, and responsive microservice architectures for the future.